So at this point, we've done quite a bit of work with differential equations, and hopefully by now, we're comfortable with the idea of a differential equation really being an equation that describes a rate of change, right? After all, a differential equation is an equation that involves a function and, one or more of its derivatives. So it's an equation that somehow describes a property of the rate of change, all right, or rate of growth of a function. So this very naturally lends itself to growth and decay models. So now we're going to get into some of the real-world applications of differential equations, of which there are many. All right, so we're going to start out with this differential equation right here, dy dt equals ky. All right, before we even go about really doing anything with this, I want us to look at what this is really quote-unquote saying. All right, so we're just going to start piece by piece here. All right, so dy dt, what does that really mean? Well, dy dt, that's a rate of change, right? So this is specifically the rate of change of y over time. So whatever y is, all right, that could be any quantity, all right? The rate of change of quantity y over time. All right, well, an equal sign, that's pretty unambiguous, right? An equal sign tells us, right, basically is, right? We translate that in English to is. And then notice what we have on the left-hand side. We have now function y itself. All right, so that quantity y, all right? So we'll talk about that in a minute, but we'll just write that in. And then there's this k here. All right, so this k, all right, and now, of course, we're going to assume that k is constant, all right, like we always seem to do, all right, because unless otherwise specified, we're going to assume that k is constant, all right, and so let's think about that, all right, dy dt equals k times y, all right, well, if it's equal to something times y, that means that it is proportional to y, right? Saying that something is equal to some number times something else, it means that those two quantities are proportional. So I'm going to say proportional to. So now if we sort of read this out, interpreting this in English, what this is really saying is the rate of change of quantity y over time is proportional to quantity y itself. That's interesting. Another way to sort of interpret this would be that the rate of change of y depends on quantity y, or that the rate of change depends on how much there is at any particular moment. So maybe start to think about that, all right, and think about what kind of function or what kind of growth that might be describing. If it's not jumping out at you, don't worry, because we're going to go ahead and figure it out, but just start chewing on that. All right, so now we're going to actually go ahead and solve this. All right, so scooting down here, all right, we're going to actually solve this differential equation. All right, and it's sort of a beautiful equation right here, nice, easy, separable piece of cake. All right, so I encourage you, all right, keeping in mind that k is just a constant, all right, I encourage you to pause at this point, try to solve this, for y equals blah, bitty, blah, bitty, blah, all right, and then once you think you have a good idea, resume the video. But spoiler alert, I'm about to continue. Okay, so we've got dy dt equals k times y. So first things first, let's separate the variables. So this will become dy over y equals k times dt, and then I will integrate both sides. And so when I integrate dy over y, that jumps out at us as the natural log of y. And then the integral of any constant will be that constant times whatever your variable is. In this case, that is t, and we're just going to put our plus c on this side just for ease. Okay, so now we've got to solve for y. All right, and so the fact that it's the natural log of y on the left tells us that we're going to go ahead and exponentiate both sides. All right, so in other words, do e to the left-hand side equals e to the right-hand side. And this is very nice because on the left-hand side, right, e to the ln y, that just becomes y equals. But then we've got this to contend with. And at this point, I can't remember how much we've discussed this situation, so I'm going to go over it just in case. All right, the key here is to use that property of exponents, right? That, for example, right, e to the a times e to the b is going to be e to the a plus b. All right, so we're just going to work that in reverse. We're going to take the sum of the exponents and translate that into multiplication of like bases. All right, so we're just going to say that y equals e to the kt times e to the c, right? And again, if that seems a little weird to you, just go ahead and verify, like, yeah, exponent rules, this works. I can totally do this. Those are equivalent. All right, and then we start thinking, right, well, the number e raised to some constant c, that's just going to be another constant. So some people like to use an entirely different constant for this, but I'm a little imprecise here, and I'll just say times some big constant c. All right, so then we will finish this up and write y equals c times e to the kt. And that's as good as we can get it. We don't know what c is. We would maybe have to solve for that with using initial conditions. K would probably be provided to us. But we've got a generalization here. All right, so this is it. All right, this is the solution to that differential equation. All right, and so you know what, we're gonna go ahead. We're gonna write this in down here, and then we're gonna make some notes about this. All right, so the solution to the differential equation, right, dy dt equals ky. In other words, for any situation where the rate of change depends on the quantity present, will look like this. Y equals some constant c times e to the kt. And now it's important to note, all right, that c in this case will correspond to your initial condition, which you would, probably be given or have to solve for using other information. And then k is what we refer to as the constant of proportionality. Just a little verbiage there. But more importantly, what I want you to look at right now is the fact that this is an exponential. The solution to the above differential equation was an exponential. And now think about how that makes sense. All right, the differential equation told us, right, that the rate of change of y is proportional to y itself. The rate of change of y depends on y, or the rate of change depends on how much is currently present. Doesn't that sound like an exponential function? After all, exponential function represents a constant percent increase, right? So for example, if I tell you that you start with, so much of a given quantity and it grows by 10% every year, that will be defined by an exponential function, right? And that 10% is going to be a different amount as your function grows. Every year, that 10% is going to be a different number, even though the percentage itself is constant. All right, so how much you add every year depends on how much you currently have. The rate of change depends on the quantity present. So this is something that I would lock into your memory, all right? Because you can go through these steps, you can derive this every single time if you wish, right? Solve the differential equation, all right? But as much as we can, we kind of like to avoid that, right? So what I would say is know that if you have a differential equation in this format, right, dy dt equals k times y, your variables might be slightly different, but anytime it's telling you that the rate of change of a quantity is proportional to the quantity itself, you can just skip all the BS and cut right to here, all right? And know that this is what your solution is ultimately going to look like. And then save yourself a bunch of time. Of course, you're welcome to go through the steps if you need to, but eventually I hope with, increased practice that we can just sort of make the jump. Okay, so let's see where we are. The next page, that's where we are. Off we go. So now on this next page, we get to some actual applications, and I think you'll be surprised to see how little calculus there actually is in these problems. Really, they become more of a pre-calculus type problem. However, you gotta know what we did on the previous page in order to even get to the easy pre-calculus stuff. All right, here it says the rate of change of y is proportional to y. Okay, so right there, I don't even care about what the rest of the problem says. When I read this, that immediately tells me, right, that I'm looking at, right, the rate of change of y is proportional to y. We just solved that, right? And we know that the solution will be of the form y equals c e to the k times t. And again, so if you didn't know what we just did on the first page, you would have to, A, be able to write that differential equation from that sentence, which may or may not be easy for you, all right, and then solve it and get to the second equation that we wrote. That takes time. But knowing what we know, we can make these jumps and life gets a lot easier. All right, so this is great. So we know, right, that our solution is going to look like this. And we can start from there now, and life is just so much easier. All right, so now notice when it says, all right, when t equals 0, y equals 250, when t equals 1, blah, 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 all of that stuff, all of that information is simply going to let us solve, all right, for c and k. We just need to find values, and we will have a complete formula. All right, so let's get started. When t equals 0, y equals 250. When t equals 0, right? That sounds a lot like an initial condition, all right? But supposing we maybe couldn't connect those dots, let's just start from scratch. So let's start with this, all right? Let's start with the information for at t equals 0. All right, we know in this equation that when t equals 0, y equals 250. Okay, so now let's solve and see what we get. 250 equals c times e to the 0. Well, e to the 0 is just 1, so, c is 250. All right, so yay, all right, that little bit there, when t equals 0, y equals 250, that told us our initial condition, which we could sort of just jump ahead and be like, oh, that's c. All right, so I'm going to go ahead, I'm going to erase this up here and pop in 250 for C. All right, now we need to solve for K somehow, and the only other bit of information that we have is what's going on at T equals 1. All right, so let's just see where that gets us. right, so this is our formula thus far. We have y equals 250e to the k times t. All right, and y is 400 when t is 1. Okay, so that's going to be k times 1, or just k. All right, so now from here it's basically just algebra. All right, so we're going to first divide both sides by 250, and we'll get 1.6 equals e to the k. And so then to solve for k, it's just natural log both sides. So the natural log of 1.6 equals the natural log of e to the k. All right, and then that will leave us with k equal to approximately 0.47. All right, that's good enough for now. All right, so now I'm going to come back up here and then insert my value for k. Alrighty, so k is, we'll just say 0.47 for now. And that is our completed formula. All right, so we can write that all out nice and pretty. We've got y equals 250 e to the 0.47 t. And now we can actually answer the question that they've asked. What is the value of y at t equals 4? Well, now that becomes almost trivial, especially since we have calculators. We've got y equals 250 e to the 0.47 times 4, which, if you do your math, should be approximately 1638.367. I'm sorry, 376. All right. So not too bad. Very little calculus, actually, right? But you do have to know the calculus at that initial step to be able to make that jump, all right? And that's sort of what's going to happen in the second example as well. All right, so for radioactive isotopes, fun, the rate of decay is proportional to the amount present. Ooh, there it is, right? There it is again. The rate of decay is proportional to the amount present. So really, you're looking through the language of these problems, all right, to sort of see what they're, to sort of decode it and put it into math speak. All right, so the rate of decay, all right, dy dt, and we could use any variables we want, is proportional to the amount present, right? Great, all right. And so we know that the solution will look like this because we're solving the same differential equation. In 1986, very good year, there was a little whoopsie at Chernobyl because a nuclear power plant in the Ukraine blew up. All right, so suppose 10 grams of a plutonium isotope were released. How long will it take for the 10 grams to decay to just 1 gram if the half-life of the isotope is blah, 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 blah. Okay, there's a lot of information here. All right, so, all right, let's pick this apart. All right, so let's see. Suppose 10 grams of a plutonium isotope were released. I would just challenge you to think about what that tells us about what we can fill in, all right, in our solution here. All right, hopefully you could connect the dots that means that at time 0, initially, right, there were 10 grams present. So in other words, all right, this is going to tell us that C is 10. All right, so from here, we can write y equals 10 e to the kt. All right, and then the whole, how long will it take for the 10 grams to decay to just 1 gram? Well, that's the actual question that we're being asked. What I am interested in right now is what we can do with this last little bit here. If the half-life of the isotope is 24,100 years, hopefully we know what half-life means, all right, besides just the video game. All right, half-life means, all right, the time that it takes for the quantity of a substance to decrease by half. All right, so using that definition of half-life, all right, we can say, all right, that it's going to take 24,100 years for that 10 grams to decay to 5 grams, right? Half-life, time it takes for it to decrease by half. So let's set that up, all right? So we know we have this, And we know that when 24,100 years have passed, our quantity will have decreased by half because that's its half-life. So we can put a 5 over here. All right? And then we can go about solving this. All right? So obviously on this side, we're going to have a 1/2 equals e to the 24,100 k. All right, so now to solve for k, we're going to natural log both sides. And use our super helpful properties of logs, all right, to simplify this a little bit. Okay, and so now to solve for k, it becomes pretty easy, right? We're just going to have k equals the natural log of a half divided by 24,100, all right, which is approximately, it's very small, 0. Oh my gosh, that's 4 zeros, 1, 2, 3, 4, 2, 8, 7, 6. And so think about what that's saying, right? If k is the constant of proportionality, right, that's basically telling us like how much the quantity decreases by every year, by what percentage, right? So this decreases by a very small, teeny tiny percentage every year, which kind of makes sense because we know that the half-life is over 24,000 years. So we should get a very small percentage here, all right? But let's come back. Let's complete our formula, right? So now we've got y equals 10e to the negative 0.4 zeros here, 2876t. And now the question asks, all right, how long will it take for the 10 grams to decay to just 1 gram? All right, well, that's easy. All right, we want there to be 1 gram remaining. So we plug in 1 for the amount present and go, go, go. Trying to solve for t. So we're going to get a 0.1 on this side. Whoops, dropped a 6 before. That's okay. All right, natural log both sides. Oops, let's see. 2876. Okay, and so then we're going to get that the natural log of 0.1 equals negative 0.0002876t. Thus, t equals the natural log of 0.1 over this super duper teeny tiny number, and that is approximately 80,062 years. And this is why nuclear disasters are so bad. All right, it's because depending on the half-life of whatever radioactive substance you were dealing with, it takes so long for the amount to decay to a either insignificant or manageable amount. So yeah, life lessons there. Okay, next page. So thus far, these problems have all dealt with just like regular exponential growth, right? If you were to graph any of the previous solution curves that we'd found for the examples, right, it would look like a regular old exponential curve, increasing, concave up, unlimited. All right, but if you start to think about that, you know, as far as the growth of like a population or something grows, it's not realistic for it to grow without bound, right? Usually at some point, there's a limiting factor. Either nature cannot support that many individuals, or, you know, there's a predator-prey model happening here, where, you know, the predators sort of keep the number of prey at bay. So basically, unlimited exponential growth is not always a reasonable model for real-world phenomena. All right? More often, what is more realistic is what we call a logistic growth model. All right, and this is a growth model that accounts for what we refer to as a carrying capacity, all right, which you may have heard of, if you've taken a biology course or something like that, right? Usually, all right, there's a sort of maximum number of individuals in a population that can be sustained, all right? So that's referred to as the carrying capacity, all right? And this type of growth, as it says, is called logistic growth, all right? And the rate of that growth is described by the following differential equation, all right? So this is called the logistic differential equation, all right? And we've got it right here. dy dt equals k times y, and then this 1 minus y over L, blah, 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 blah. Okay, so few things that we need to note here, all right? In this equation right here, all right, k is obviously a constant, and guess what else is a constant? L, all right? L here is the carrying capacity. So whatever that number is, that is what is going in for L. So I want us to think about a few different situations, all right? So we need to remember what everything means, right? K is a constant of proportionality, L is the carrying capacity, T is time, but what is Y? Y is the current quantity, current amount, current population. So what I want us to do now is remembering that Y up here sort of represents the current population, right? Because it's probably going to be population in this context. I want you to think about, all right, the conditions, right, the relationship between Y and L under which the population will grow or the population will decrease, all right, knowing that L is the carrying capacity. Now, intuitively, all right, we would sort of feel like, well, if your population is less than your carrying capacity, your population is going to continue to grow. And that is absolutely the case. But let's think about why that's true mathematically based on this differential equation. All right, so if Y is less than L, if your current population is less than your carrying capacity, you're going to have a growth scenario. How come? Well, that's because if Y is less than L, that means that this entire fraction here is going to be less than 1, right? Which means that this quantity is going to be positive, okay? So if Y is less than L, dy dt ends up being greater than 0. And if the derivative of a quantity is positive, it's growing. So we can now extend that to the flip case, right? If the current population is greater than your carrying capacity, obviously, intuitively, you're going to have a decay situation, right? Your population's going to start decreasing to sort of balance back with the carrying capacity. But let's think about why that's true mathematically. All right, so same deal. All right, if Y is greater than L, the fraction Y over L is now larger than 1, which means that 1 minus that is now negative. So your derivative is negative. And if your derivative is negative, your quantity is decreasing. Now, as much as I hate to say this entire equation right here, all right, this right here is just something you're gonna have to know, because deriving it is a giant pain. And you'll see that in just a moment. All right, so I would sort of lock that in your brain. Keep in mind what is where, right? Notice it's y's everywhere, right? dy dt, k times y, y over L. And if you think about it in terms of carrying capacity, right, you know, everything depends on what the current population is. How the function is going to behave depends on what the current population is. So it's all about population, okay? But let's get to it. Let's actually solve this thing. Okay, so coming over here. All right, we're eventually going to put our final answer in the box there, but we are not there yet. All right, so let's start with our differential equation. We've got dy dt equals k times y times 1 over y minus L, and again, or y over L. The whole key to this is going to be remembering what is constant, right? It's going to make it much simpler. All right, so first things first, all right, we're going to separate our variables, all right? And I'm actually going to label what I'm doing because it's going to be a lot of work, and I just don't want us to lose our place, all right? So first things first, separate our variables. That's the name of the game. All right, so to bring all our y's onto one side, I'm just going to divide out like everything except the k. All right, so I'm going to have dy over this entire big honkin' thing equals k dt. And so then the next step is going to be to integrate both sides. All right, so really, we're looking to do this right here. And the right-hand side is the cinch, but, I mean, you are welcome to try the left-hand side, but something should bother you right out of the gate, and that's that on the left-hand side, we basically have the integral of a product, all right? Y times 1 minus y over L. Now you can distribute the y, sure, okay, and try to integrate that, but then you end up with this binomial in a denominator, and it's this huge mess. Basically, with the techniques that you currently have, you're not going to be able to integrate this. However, the technique that this requires, we will be learning later in, I think it's chapter 8, all right? So you will learn how to do this, but bottom line, we're going to sort of bypass, all right, the method, and I'm going to sort of give it to you, all right? But eventually, you would be expected to know how to do this. All right, so basically, I'm going to give you the shortcut, all right? And the shortcut right now, so let's see, is that the left-hand side, when we use this method, and by the way, the method is called, all right, partial fractions, all right, which is honestly an Algebra 2 technique. So using partial fractions, we are able to simply rewrite the left-hand side so that it becomes something that we are able to integrate. All right, so when we use partial fractions, we're able to rewrite the left-hand side like this. So we're going to have, all right, 1 over y plus 1 over L minus y dy equals k dt, okay? And again, don't worry about how, necessarily, this here becomes equivalent to this. That's just a partial fractions decomposition, and we will be learning it. But, maybe take my word for it for now. Or if you know how to do partial fractions, figure it out for yourself and confirm that I've actually done this correctly. All right, so now when we integrate this, all right, this actually becomes pretty easy because we can just do this term by term. All right, the antiderivative of 1 over y is going to be, the natural log of y. All right, and then the antiderivative of 1 over L minus y, well, that's going to be, all right, the natural log of L minus y, all right, but we have to take into account the fact that the y has a coefficient of -1, so that when we do chain rule, we would be multiplying everything by a -1, so that's just going to change the sign out front to a minus the natural log of L minus y. All right, and so then the right-hand side is super simple, right? That's just going to be your KT, and then we'll throw our constant of integration on the other side, call it a day, and now the name of the game just becomes solve for y. Which honestly, like, this is now the hardest part, okay? All right, so first things first, I don't want to exponentiate both sides just yet because I don't have a single natural log, right? Usually your goal is to get a single natural log, right? Nice and tidy, then exponentiate both sides. So I don't have one now, but I can use log properties, right? The difference of two logs is equal to the single log of their quotient. In other words, I'm just going to use this little helpful property here that, like, the natural log of A minus the natural log of B is the natural log of A over B. And that'll get me to a single log. Hooray! So let's do that. So applying that to the above equation would give me the natural log of y over L minus y equals KT plus C. And now we can go ahead and exponentiate both sides, right? So we'll say e to the natural log of all this business equals e to the KT plus C. All right, and then of course the e and the natural log on the left are going to cancel out. So you're going to have y over L minus y equals, and then I'm going to use that same little trick on the right-hand side, e to the KT times e to the C, and really just call that e to the C another constant and put it in front, okay? And in fact, let's give me a little bit more room to work with over here. So equals CE to the KT. Fantastic. All right, so here's the thing though. Got to remember, the challenge is to solve for y, all right? And maybe you can kind of see that this is becoming a little bit complicated, but it's going to be okay. So first things first, I'm just going to multiply both sides by the denominator of the left-hand side so that I get CE to the KT times L minus y. And I need to bring the y on the right over to the left. The only way to do that, all right, is to distribute it, right? All right, or to distribute the CE to the KT into the parentheses so that that L minus y, right, the L and the y become separated. All right, so next I'm just going to distribute the CE to the KT into the parentheses. So y equals CE to the KT times L minus CE to the KT times y. And now I can add the y term on the right back over to the left so that I have y plus CE to the KTY equals CE to the KT times L. And in order to now isolate the y, I can just factor it out. So that's going to be y times the quantity 1 plus CE to the KT equals CE to the KT L. All right. And then from there, all we're going to do is just divide both sides, right, by the whole 1 plus all that junk to isolate y. So y equals CE to the KT times L over 1 plus CE to the KT. All right, now technically at this point, all right, we have solved for y, and that's wonderful. All right, but this ultimately is not the format that we're going to leave it in. We want to clean this up a little bit so that, I mean, because first of all, I have like the CE to the KT in 2 places. It's just not pretty enough yet. I hate to say it. I don't want to hold equations to unrealistic beauty standards, but we're kind of all about that in math. So, all right, I'm going to come up here, all right, and in these next several steps up top, all right, we're just going to put this into a proper format. All right, so from here on, it's just all about formatting. All right, so first off, let me make a note of what I currently have here. So currently, we have y equals CE KT times L over 1 plus CE to the KT. All right, so the first thing that I'm going to do is divide, all right, both numerator and denominator by CE to the KT. How would you know how to do this? You wouldn't necessarily. All right, so don't worry about that so much. So I'm going to divide the top by that, and I'm going to divide each term in the denominator by that as well. All right, so up top, all I will have left is L. On the bottom, all right, I will have 1 over CE to the KT plus 1. But now, here's the thing, all right, we don't really like the whole fractions and fractions type thing. So instead of saying 1 over CE to the KT, all right, I'm just going to make the exponent negative, and then it's going to look a little nicer. All right, and actually, whoops. All right, so technically, all right, what we would have here now is 1 over C e to the negative KT plus 1. But guess what? 1 over a constant is still just a constant. So we can just say y equals L over some other constant C. Again, I'm being pretty imprecise here, but ooh, well. All right, CE to the negative KT plus 1, and then really the finalized format that you'll see it in is y equals L over 1 plus CE to the negative KT. So that was a lot of work. This is the solution to the logistic differential equation. And maybe you can see now why these are both just kind of things that we decide and agree that we're gonna know. Solving it is a giant pain. All right, so this, all right, this is what you are going to put, all right, in that box at the top. I'm not gonna scroll all the way back up to the top and put it there because explain everything is being a little wonky for me right now. All right, and every time I scroll, something weird happens. All right, so you can put that in the box, and then I'm just gonna make a note that, of course, you know, L, as we said before, all right, that's going to be our carrying capacity. All right, K is the constant. C, not necessarily your initial condition, all right? And we'll see that in some of the example problems that we do, all right? But I would just know that when you see a logistic differential equation, this is its solution, all right? And so we'll do a short example on the next page, and that'll be that. See you there. All right, so in this example, it says 40 elk are released into an animal sanctuary after 5 years. The population is 104, and the commission there believes that the sanctuary can support no more than 4,000 elk. Estimate the elk population after 15 years. Oh my goodness, this problem, if we did not know that logistic growth was a thing, it would be near impossible, in my opinion. All right, so what's the key phrase here that we need to latch onto in order to do this problem? All right, well, I would say that the commission at the sanctuary believes it can support no more than 4,000 elk. That to us sounds a whole lot like a carrying capacity. And because the growth, right, refers to a population, all right, that growth is most likely exponential. So the fact that this is exponential growth and there is a carrying capacity, all of this to us implies logistic growth. All right, so let's write that out. All right, so we know that if this is a logistic growth model, all right, we should know the differential equation and we should know the solution. And now here's the question. Which one of those things do we want to work with? Well, it says estimate the elk population after 15 years. So the question becomes, would population be described by like a, by a dy dt or just a y, right? dy dt would refer to the rate of change of the population, so it's not that. All right, so when we estimate the elk population after 15 years, we'll be working with quantity y. So that tells us I actually just want to write out the solution, all right, to the differential equation. I don't need the differential equation at all, all right? But because I know that the growth model is logistic, all right, that's what directs me here. So we know it's going to look like y equals L over 1 plus CE to the negative KT. And guess what? We already know that the carrying capacity is 4,000. So we can go ahead and write 4,000 over 1 plus CE to the negative KT. And then in order to find a complete formula for this, which we will need to predict the population, in order to find a complete formula, all we will need to do is find values for C and K, just like before. Okay, so, all right, now careful. It says 40 elk are released into an animal sanctuary. That might be tempting for you to say, so C is 40 because C is our initial amount. But remember, this is a different structure. This is not the original differential equation that we started this packet with, right? This is a logistic growth model, so this is different. All right, so let's just go ahead, all right, and let's use this information here. Okay, that, all right, that initially at time 0 there were 40 elk. All right, so I'm just going to write that out. At time 0. All right, so we know that the population was 40. When t was 0. So from there, we just kind of go. And that'll be e to the 0, which is 1. So you'll end up with 1 plus c, right? And then multiply both sides by 1 plus c. And then, so 1 plus c equals 4,000 over 40, which is going to be, I feel like I should be able to do that a little bit easier. Is that 100? All right, well, let's cross our fingers, right? Therefore, c is 99. So notice, c is not 40, right? So here, c is not the initial condition. All right, but, so now we can go ahead and pop that in right here. So from here, we now sort of advance to y equals 4,000 over 1 plus 99, e to the negative kt. And then we just need to find a value for k. And let's see, what other information can we use? Right, after 5 years, the elk population is 104. All right, so let's use that next. All right, so at t equals 5, we know some stuff. All right, so the population at that point is 104. Thus we write. So 1 plus 99 e to the negative k times 5. Okay. And then it's just a matter of solving for k. Now, I feel like we've done enough of these problems now, right? Solving an exponential. It's a little bit of pre-calculus. All right. So I would say pause the video if you feel like you really want to work this out for yourself. It's just solving an exponential, right? Natural logs, woo! All right. But at this point, I'm just going to kind of give it to you to save ourselves some time because we've been at it for a little while. If you do this properly, you should find that k is approximately 0.194. All right, so that when we build our completed formula, we have y equals 4,000 over 1 plus 99e to the negative 0.194 t. And I know with the negative value for k, it might look like the function is decaying, but keep in mind this is in the denominator. So something that's, sort of negative in the denominator is analogous to having it positive in the numerator, right? So just keep that in mind. It looks like it's decaying, but it's not. All right, so we've got our formula. All right, so then now the last step is to just use that formula to predict the population after 5 years. And that's easy, right? That's just going to be plugging, or I'm sorry, not 5 years, 15 years. That's just going to be plugging 15 in for t. And honestly, the hardest part of all of this will be making sure that you do all of that correctly as far as order of operations goes in your calculator. And if you do that all correctly, you will get 625.67, which, depending on your philosophy here, you could either round up or down. I'm going to say that 0.67 of an elk does not a whole elk make, and so I'm just going to say 625 elk. So there we go. There we have it. And now aren't you looking forward to partial fractions? Okay, over and out.